Okay, so Unit 10, the fundamental theorem of calculus. This is the the basic thing about integration. Okay, in the last unit, Unit 9, we saw how to compute from a given function its primitive. That is the function that when you differentiate it, you get the function that you were given at the beginning, right? The fundamental theorem of calculus actually relates those primitives to the calculation of integrals. Okay, so what are integrals? We're from the early Greeks, from Archimedes and early on. Well, there was in the ancient Greece, there was a big focus in geometry, right, in computing geometric variables, right, and solving geometric problems. And so one of the problems was to compute, for instance, areas and volumes of forms, right? So if you have like a square, it's easy to compute its area, right? We know the formulas. If you have a triangle, you know how to compute those. And the Greeks actually developed quite a lot of methods to find the area of any polygonal form, right? The problem became what happens when you have forms with curved surfaces, right? And for our purposes, that means what happens if you have a function like this, and if you want to compute the area between this function and the x-axis, right, between 2 points A and B, what's the value of this area? Well, that's where the integration comes in. Okay, the integration, an integral is to compute the area under the curve of this curve strip. Okay, and so the basic method that the Greeks developed and that was refined during the years is that, well, we can actually approximate this area by dividing this interval into pieces, and then in each piece of this interval, right, we can approximate this area by approximating the area of the function here, right? Or sorry, the height of the function. Okay, typically with rectangles. Okay, and then if we get to very, very narrow intervals here, then the area that we get by summing the area of these rectangles will approximate very well the area under the curve, right? That's this idea. So for instance, suppose we want to compute the area behind the function x squared, right, between 0 and a point A. So what's this area? Okay, so the idea is, well, we can divide this let's see, this interval 0A in n different points, right? And so each one of them has width of A divided by n, right? So you have this interval that starts at 0, right? Or let's see, the points that divide the interval are 0, an, then you have 2an, 3an, and so on, right? Until you get n minus 1 over n times a and a, right? Those are the points. So we want to get an approximation of the function in this interval, and we're going to see, well, this is in this interval between 0 and an, we're going to get the highest value of the function, right? Which is this is x squared, right? So the function of x at the rightmost point k an, right? So k goes from 0 to n is k squared a squared divided by n squared, right? Now the sum, the area of each one of these rectangles, the kth rectangle, right? The area k is just this function times the height, right? So it's times the width, right? N squared, and then you have a divided by n, right? This is the width of each of these intervals, right? So you have a cubed divided by n cubed times k squared, right? And now the total area is the sum from k equals 1 to n of this value, right? A cube n cube, sorry, this is n cube to k squared, right? And so a cube and n cube go out of the sum, and you have the sum from k equals 1 to n of k squared. And this is the sum of the first the squares of the first n natural numbers, and we've seen this before in unit 1. This is n times n plus 1 times 2n plus 1 divided by 6, right? So this sum is equal to a cube divided by 6, and then this is equal to n times n plus 1 times 2n plus 1 divided by n cube, right? Now the idea that we were saying is that, let's call this a n, right? This depends on the number of intervals. Now the actual area, if this procedure works, is what happens when the number of intervals that we take goes to infinity, the limit when it goes to infinity of this area a sub n, right? And so this limit is a cubed divided by 6, the limit of n plus 1, 2n plus 1 divided by n cubed, right? Let me erase this. Okay. This limit, if you see, this is n times n plus 1, this is goes like n squared, and this is like 2n cubed divided by n cubed. This limit is 2. So this area is a cubed divided by 3. Okay, that's the area between 0 and a of below the area the function x squared. Okay.